All right. Hello, everyone. Welcome to VSPG. Today we're hearing from Dr. Johanna Salminen talking about the paleomagnetism of Mesoproterozoic mafic dykes of Congo, São Francisco, implications on the transition from Nuna to Rodinia supercontinent. So I'll introduce Johanna for us today. Dr. Johanna Salminen is an associate professor of solid earth geophysics at the University of Helsinki and has been leading the paleomagnetic research in the Solid Earth Geophysics Laboratory of the University of Helsinki since 2014. From 2021 to 2023, she was also head of the Geophysical Laboratory of the Geologic Survey of Finland. She earned her master's in geophysics in 2004 and a PhD in solid earth physics in 2009 from the University of Helsinki. Her research interests lie in continental reconstructions, Precambrian supercontinents, deep time evolution of the Earth, Cenozoic magnetostratigraphy, environmental magnetism, and biomagnetism. Her professional recognitions include an Academy of Finland Research Fellowship and the Early Career Scientist Award by the International Union of Geodesy and Geophysics. She's also leader of the Deep Time Digital Earth Paleomagnetism Working Group. So thank you, Johanna. It's great to have you here today presenting for us, and we're really looking forward to what you've got. So please go ahead and get started with your presentation.
Okay, thank you so much, Alex, and thank you very much for inviting me to give the presentation. And today I will talk you about Paleomag of Mesoproterozoic mafic dykes from Congo, São Francisco, as Alex introduced. And this is just briefly showing what all the different topics that I'm studying at the moment, and the red thread in my research in all of these topics is magnetism of nano-sized magnetic minerals. And this magnetism has many different applications, and this poster shows that we do many of them in the solid earth geophysics lab that I run. And the lab has been built by Professor Lauri Pesonen, who retired more than 10 years ago from the lab. So these are all the topics that we are studying in the lab, and the supercontinents are close to my heart, and I was very happy that I got this invitation to give the talk to you today. So then back to the topic of the talk, and this is the outline. So since I didn't know the background of the audience, I start very far. So I first introduce you to the supercontinent cycles and the role of them in Earth system. Then I'll introduce you to the tools that we use to reconstruct these supercontinents. I introduce Paleomag. Then briefly some other tools that can be used for reconstructions. Then I outlined some motivation to study Congo, São Francisco, and its participation in Nuna supercontinent. Then I will show you a case study from 1.38 GA Virey dike swarm in Angola, which is part of the Congo Craton. And this is from the paper just recently published. And then I end the talk with the conclusion. So I start very far by showing the Pangea reconstruction of Alfred Wegener. So he was the first to propose the existence of the youngest supercontinent, Pangea. And this was already at the beginning of the 20th century. And he based his suggestion on the similar geology, plants, fossils, and animals on different cratons. And he suggested that Africa and South America have been close to each other at some point in geological past. But this required that the continents were moving laterally And at the time when he was proposing this, only the vertical motion of continents was accepted, and he could not explain what was making the continents to move laterally. And after his death, this theory of Pangea and lateral movements was abandoned. And actually the technology of World War II and paleomagnetism was needed to before the lateral movement and the plate tectonics was accepted. And this is the classical map of the marine magnetic anomalies of west coast of North America by Ruff and Mason. And this provided information that the new crust was forming at the spreading center of the mid-ocean ridges. And this also proved the evidence of the operation of plate tectonics. And this map also has another fundamental observation. So it shows that the rocks can record the direction of Earth's magnetic field and that the direction changes polarity, and this black and white represent opposite polarities of the magnetic field. Then in the early 50s, researchers from Cambridge started to do paleomagnetic studies, and they found that the rocks of different ages from roughly the same area in Britain showed different apparent magnetic pole positions. And these poles of different ages are forming so-called apparent polar wander path. And these pioneers first assumed that this meant that the Earth's magnetic field had departed significantly from its present-day position, which is close to the rotational pole. And same thing was a little bit later also noted for North America. So it was also noted that the different age poles were forming apparent polar wander paths. And but when the researchers were reconstructing North America and Eurasia according to the reconstruction of Pangea, they noted that these two apparent polar wander paths were overlapping. So this actually proved that the continents have moved over the time. And this also shows that the paleomagnetism is a very powerful tool when studying the relative continental drift and building the reconstruction. And it was also the key when the theory of the plate tectonics was accepted. So the existence of Pangea was accepted at the 60s, and it took almost 30 years until the other supercontinents prior to Pangea were acknowledged. So first Rodinia at 90s, and then Nuna or Columbia. It has several names. It was the Mesoproterozoic supercontinent was accepted at 21st century. And in the past 10 years, it was realized that the supercontinents amalgamate and break up in cycles, roughly 600 million years. And these cycles are also seen in the global peaks in isotopic age determinations. And so then I'm outlining the reasons why to care about the supercontinents, why to model the paleogeography. So this diagram shows the assembly of lithospheric blocks from Archean supercratons to supercontinents through Earth's history. And weathering of these assemblies stripped CO2 from the atmosphere. This initiated cooling, which resulted global continental glaciations at the beginning and end of Proterozoic. And these events are also linked with the atmospheric oxygenation events and temporarily also on the emplacement of number of large igneous provinces on low latitudes and also with the evolution of life. And in addition, the increased rate of cooling of mantle has been temporarily linked with these events, especially with the breakup of supercontinents. So there are clearly significant links between supercontinents, so lithosphere and mantle, and also the evolution of the atmosphere and life. And the focus of this presentation will be reconstruction of Nuna supercontinent, and a little bit also about the onset of Rodinia. So then few words about paleomagnetism. So I'm using Paleomag data in my research, and I wanted to highlight the importance of the paleomagnetic data with this figure. So the time goes here from present towards the Hadean, and the circles on the x-axis indicate the abundance of rock record, and then the y-axis shows the depth penetration of some geophysical methods, which reveal the present-day structure and physical properties of the Earth until the inner core. And then there are some people who say that there is no data available to fill this gap, and intuition and numerical geodynamic modeling must be used. But they forget the paleomagnetic data. And as I mentioned, the paleomagnetic method was the one that proved the operation of plate tectonics, and it can be used to explore the tectonic regime. And the Paleomag is also the only method which provides quantitative data for paleogeographical plate reconstructions, and therefore also data to study the kinematics of the supercontinent cycles. And because of this, it also provides data for geodynamic models. And Paleomag can also be used to explore the geodynamo and the planetary evolution, especially the evolution of the core and the formation of the solid inner core. So Paleomag is a very useful tool when exploring the processes of the mantle and core. And then how do we use it? So we use it for reconstructions, and the Earth has a magnetic field which is caused by the self-sustaining dynamo processes in the core, and this field has a dipolar nature. And polarity of this field changes few times per million years. And this magnetic field can be recorded by rocks. And in Paleomag, we are using a geocentric axial dipole model for the field. And as the inclination of the field varies depending on the latitude, then by measuring the inclination, we will get the ancient latitude of the craton. And this is the base of the supercontinent reconstructions. But due to axisymmetry of the geocentric axial dipole model, we do not get any information of the longitude. And in addition, for Precambrian, we do not know the actual polarity of the field. So then for Paleomag studies, it's very important that we sample the rocks that can record reliably the Earth's magnetic field direction. And the best recorders are the mafic intrusions, as they contain iron-rich minerals that can record the direction. So for Paleomag study, we usually sample, for example, if we sample mafic dykes, we always sample several intrusions that share the same age. And then okay, so this is actually showing how the Earth's magnetic field direction is recorded by these igneous intrusions. So at the beginning, when the lava is still hot, and when it starts to cool, the temperature of course decreases, and at some point the minerals are crystallizing, and when it further cools to some specific temperatures, magnetic minerals can lock in the direction of the Earth's magnetic field. There are few different magnetic minerals, for example, magnetite, and magnetite locks Earth's magnetic field direction around 580 degrees of Celsius. And different magnetic minerals have different temperatures where they lock in the direction. So in ideal situation, we can measure this direction in the lab from the rock samples. But when we are dealing with Precambrian rocks, very old, there is possibility that these rocks have suffered many different geological processes that could have left a mark on this magnetization. So very often the rocks contain several or at least one type of secondary magnetization. And then the magnetic direction that we measure is the vector sum of these different magnetic directions. But if we are lucky, we might be able to separate the primary magnetization direction from the secondary ones. And there are some tests to verify if one is dealing with the primary or secondary magnetization. So for paleomagnetic study, we sample, for example, in this case, we were sampling mafic dykes in Bornholm. So we sample several intrusions that we think are coeval. And we take the samples, we measure them in the lab, and we calculate the mean direction for each intrusion. And then from this measured direction, we define a paleomagnetic pole, and then from paleomagnetic poles of each different intrusion, we defined a mean paleomagnetic pole. This is an example of a paleomagnetic pole defined from the Australia. So red Australia is in its present day position, and this red paleomagnetic pole has been defined from Australia. And when we reconstruct the position of Australia based on this paleomagnetic pole, we take the pole on the rotation axis, and then we rotate the Australia using the same angle. And as the field is axisymmetric, we do not know the longitude of the craton. So the craton can be actually positioned on the same latitude, well, on different longitudes on the same latitude. And then also, as we do not know the polarity of the field at the Precambrian, there is also another polarity option. So the defined pole would be reconstructed on the southern rotation axis, and then this takes Australia to the other hemisphere. So we always have these two polarity options. And this is just to show that paleomagnetic community is very active in data curation and keeping up the database. And we always discuss about the quality of the data within the community. And for this, Finland and Solidar Geophysics Lab has had very important role. Lauri Pesonen was the key person in advancing paleomagnetic data curation worldwide. And he and Sten-Åke Elming and Trond Torsvik and few other paleomag researchers started Nordic paleomagnetic workshops at ATs, and this started as a Nordic event. And now we also invite international scientists to these events. But these events are organized, or the workshops are organized roughly every 5 years. And outcome of these workshops very often lead to publication with very, very high impact. And I have been participating these meetings already 20 years since my undergrad, and I will be organizing the next workshop in Finland 2026. And this is actually showing the criteria that we use when we are evaluating the quality of the data. And we use the criteria by Rob van der Wouw, and those criteria were refined slightly few years back, initiated by Joe Meir. And the criteria are listed here. There are 7 criteria that we are checking. And if the data fulfills the criteria, it scores 1. If it doesn't, it scores 0. And so we are checking if the data is coming from the intrusions that have been dated, and then we evaluate the techniques and statistical analysis of the data. For example, if it's coming from the mafic intrusions, there should be at least 8 or more separate sites with 3 or more samples per site, giving the same direction. Then we also evaluate the remanence carriers, so do some rock magnetic study. And then this is very important criteria, as is also the age. We evaluate if the obtained magnetization is primary, and there are some paleomagnetic field tests to do that. Then we also check if the data is coming from the structurally controlled units, and then if there is presence of both polarity directions, and then we also check if the pole is overlapping or not overlapping with any younger poles. And from these criteria, the criteria number 1 and 4 are the most important. So the age and the primary magnetization. And if the data fulfills both of them, it's grade A pole. And if the data fulfills either one of these plus a few other criteria, it's grade B pole. And both of these are high quality data. Okay, so then if we have this high quality data coming from several different intrusions, we can form apparent polar wonder parts. And if we have several poles from one craton, they form the apparent polar wonder parts. And by comparing these APVPs, we can test if continents have been traveling independently or if they share a common drift. So this is an example of a paleomagnetic test of the common drift. So the upper part of this diagram shows 3 separate cratons, A, B, and C, and the lower part shows the apparent polar wonder parts. And if the cratons were drifting together, then their poles coincide during the interval they were drifting together. And if the ocean was opening between the cratons, then the APVPs are departing. And this is the test, kind of test that I'm using in this case example that I will be showing to you. And this is very typical thing for paleomagnetic research. And this also fixes the relative longitude of the cratons. We do not get the absolute longitudes, but with this test, we get the relative longitudes between the cratons. Okay, so then some other tools for reconstructions. We can use, of course, the geological piercing points and the matching geology. Very widely used tool is to match the fragments of large igneous provinces, and then a large igneous province record is also used to produce so-called magmatic barcodes, and this is an example of Siberia and Laurentia, and each black line indicates a lip event, and this diagram shows that the Siberia and Laurentia are sharing similar kind of magmatic lip barcode between 1.9 and maybe even 0.7 GA. And Richard Ernst and Walter Plieger were proposing that this kind of comparison of magmatic barcodes can be used to study the nearest neighbors. And then, of course, when we use this, the geochronology is very important. Okay, so then to the motivation to study Congo, São Francisco. So Congo and São Francisco cratons are made of several Archean and Paleoproterozoic nuclei that are welded together by Paleoproterozoic belts. And this assembly here is dates back to 2 billion years ago with the closure of the major Paleoproterozoic orogenic belts. And then this entity records a long and complex geological history, and this history includes the time window of all the proposed Precambrian supercontinent assemblies until the breakup of Africa from South America during the opening of the Atlantic. And Congo São Francisco has been considered a main building block in Gondwana due to its central location. And Congo São Francisco, but participation of this landmass to Precambrian Rodinia and Nuna supercontinents has been considered controversial. And this presentation focuses on Nuna, and the paleogeographical reconstructions I will show to you are done using paleomagnetic data, and I will just briefly introduce some of our results from 1.5 GA Curasa dykes in São Francisco, and then the main part will be concentrating to the Virey dykes from the Congo. And the arrows in this map indicates the sites for paleomagnetic poles for Congo São Francisco. And as you can see, there are not too many of these. And yes, as I mentioned, I will concentrate to our new data for the Congo craton. And in the reconstructions that you will see in the coming slides, I will show this kind of color scheme. And this map shows the Precambrian part of now existing continents with colors. So Laurentia with the light blue, Baltica pink, Siberia gray, North China, South China orange, then India, Australia and East Antarctica cratons with brown, and then Congo, São Francisco with dark green, West Africa light green, Amazonia yellow, and Kalahari pale purple. And in initial models of Nuna, Congo São Francisco was shown as a part of Atlantica, so-called Atlantica landmass, together with Amazonia, West Africa, maybe Rio de la Plata. And this Atlantica landmass was separate from other parts of Nuna. And 96 Rogers proposed that this Atlantica landmass persisted united for more than 1 billion years until the formation of Gondwana. So this reconstruction of Atlantica is exactly same as the reconstruction of these cratons in Gondwana. And if this is the case, it would challenge the existence of relative horizontal motions and therefore the existence of modern style plate tectonics during the Precambrian. However, later this Atlantica landmass was challenged by paleomagnetic data from Amazonia and Rio de la Plata cratons. And here is the study that challenged the Atlantica. So I will walk you through this figure. So this data shows Congo, São Francisco, Rio de la Plata, Amazonia, and West Africa in their Gondwana configuration. And on the right-hand side, the paleomagnetic poles from these cratons have been shown in the similar relative reconstruction as the cratons here. So the poles have been rotated according to this reconstruction. And if this reconstruction would be supported by paleomagnetic data, then the coeval poles from the different cratons should be overlapping. And as the coeval poles are not overlapping, it indicates that the paleomagnetic data does not support exactly this type of configuration of these cratons. However, it's not shown here, but this data presented here, it permits the existence of landmass, including Congo, São Francisco, Amazonia, and Rio de la Plata, but not in this type of relative configuration, but in different type of configuration. So then later, Congo, São Francisco has been reconstructed also with other cratons during the Nuna cycle. And these reconstructions are based mainly on the geological evidence and mainly on the barcode matches of the dike swarms. And a connection with Siberia, so Congo, São Francisco, and Siberia was proposed based on the barcode matching at 1.5 and 1.38 GA by Richard Ernst and others, 2013. And they also provided a reconstruction of Congo, São Francisco, and Siberia at 1.38 GA. And they used paleomagnetic data which was not very high quality for Congo. They used the data from Kynene complex, and this data scores only 2 out of 7 criteria. And then for Siberia, they used the pole which is coming only one single dike. So this is something that we called virtual geomagnetic pole, and it does not average out the secular variation of the geomagnetic field. They had the data, and you can try to do reconstructions, but the data was not the highest quality. So then later, Pisarevsky et al. 2014, they used this relative configuration of Congo, São Francisco, and Siberia in their 1.5 GA Nuna reconstruction. And they kept Congo, São Francisco, and Siberia very close to the proposed 1.38 GA location. And at the time when this reconstruction was done, there was no 1.5 GA paleomagnetic data for Congo, São Francisco. And then a few years later, me, Dave Evans, Ricardo Trindade, Elson Oliveira, Elisa Piispa, and Alexei Smirnov, we provided a high quality 1.5 GA data from Curaçá mafic dikes from São Francisco, from Brazil. And we used this data to reconstruct Congo, São Francisco in close proximity with Siberia and Baltica. And this is also supported with the coeval lips for these cratons. And then this is just to show that in this reconstruction, we are showing Baltica and Amazonia in Samba type model, and this model was proposed by Åke Johansson. And if this model was accepted, then Congo São Francisco was also connected with Amazonia at 1.5 GA. And this is just to show that even though Congo and Amazonia are close here in Nuna, this relative these configurations are relative configurations of these cratons are different in Nuna and in Gondwana. So then also a little bit later or earlier, some authors have proposed also connection of Congo, São Francisco, and West Africa. And so there is a matching magmatic barcode at 1.38 and 1.5 for these cratons. So then testing the kinematics and building up the reconstructions for Nuna cycle for Congo, São Francisco has been challenging because there has been a very little paleomagnetic data for this. And then our 1.5 Kurasa pole was the first pole for Congo for that interval. And this is actually a very typical diagram what we are producing in our Nordic paleomagnetic workshops. So we list the cratons here on the left, and then the time or the age of the pole is going here. And then the high quality poles are shown in these diagrams. The A grade poles are shown with the bigger symbol and the B grade poles with the little bit smaller. And as you can see, for Congo, there has been only one high quality pole. And that was the motivation for our work in Angola, to fill the gaps in the data and to build up the reconstructions of Congo, São Francisco in Nuna. So then to the case study. So this is I will briefly go you through our recent paper published from Congo, São Francisco, and this is a group effort. And so we went to Angola. We had 2 field seasons there. 2016 we were there with Dave Evans, Richard Hansen. 2018 we were there with Dave Evans and Ricardo Trindade. And we were sampling the Virey dykes in Angola. And the crystalline basement of this Angola Kasai block was intruded by these Mesoproterozoic dykes and set of mafic sills around between 1.4 and 1.38 billion years ago. And then we did our preparation with the Google Earth map, and we were sampling 32 west-northwest trending dykes in Angola. And these dykes are part of the more than 400 kilometer wide dyke swarm. And the sampled dykes, they cut the 1.8 GA granite plutons and schist gneisses. And these dykes trend prominently towards the Kynene complex, 1.38 Kynene igneous complex, but they have not been obtained to cut it. And then this is the site of the one thick dike that was dated, and as the dike is very close to a town called Virey, we are calling this dike swarm Virey dike swarm. And when we were doing our sampling, we at the 4 sites we were sampling also baked and unbaked host rocks for attempting to do the baked contact test, which is one of the paleomagnetic tests to study the primary nature of the obtained magnetization direction. So this is the geochronology of this Virey dike. The dike was 50 meters wide. The battaliate cranes were separated, and the cranes were combined. 5 to 7 cranes were combined into 3 fractions. And the 3 fractions analyzed form a cluster just below the Concordia regression. And since 2 of the fractions marginally overlap with the Concordia, the weighted 207, 206, the weighted mean of 207 and 206 dates were used. And this results in age of 1385 plus minus 5 MA. And this is almost identical with the upper intercept age. And this age also matches with Cunene intrusion and associated silicic magmatism age. And so as the Virey dikes have not been obtained to cut the Cunene complex, we were suggesting that they could be part of the plumbing system for the complex. And as the emplacement of the Cunene complex is coeval with the bimodal magmatism at the Gibaran, roughly 1,000 kilometers away from the Cunene, we propose that these two form the craton-wide Cunene-Gibaran large igneous province. So we provided a new age for the magmatic barcode of Congo, São Francisco. It is matching the Cunene age. So then from the sampled over 30 west-northwest trending dikes, we identified 12 dikes, so 12 separate cooling units that preserved either a intermediate northwest up or intermediate steep southeast down directions. And when the polarity of the southwest down directions is inverted, it's evident that the obtained directions are very scattered. And this same scatter is also seen in the scatter of the calculated virtual geomagnetic poles. And of course, the scatter of the data lowers the quality of the paleomagnetic pole. And then we wanted to see if there could be actually several different swarms instead of one swarm, and one way to do it was to study some geochemistry, and this is actually geochemistry is not my field, so the data is from Martin Clausen, and I apologize if I'm not explaining it on the best way. So so the bulk rock geochemistry was made for 11 of these 12 dikes that were providing paleomagnetic data. And the analyzed samples show very large scatter in total alkalis and silica. And these are ranging from more alkali to tholeiitic basalts. And then in this Pierce classification diagram, all samples cluster as non-alkali basalts. And then when we plot the spidograms, the 7 more alkali dikes are overall slightly more enriched in incompatible elements compared with the tholeiitic basalts. And then this black indicates the dated dike, and while the dated dike, this plotted as a tholeiitic basalt, it also shows abnormally low concentration of most incompatible elements. And we were explaining this by the accumulation of olivines and plagioclases within this sample. So, but despite the lowering of physical lowering of these elements, if we sort of lift the data and compare it with the others, the shape is the same. So we are proposing that these are part of the same swarm. And then so the data is scattered, but we propose that it's from the same swarm. Then we try to do the baked contact test to study the primary nature of magnetization. And this diagram shows how the baked contact test works. So you obtain direction from the dike, and when the magma was coming to the host rock, it was heating it, and in the elevated temperatures, when the magma cools, it locks in the same direction as the dike. And then far away in the host rock where this heating was not happening, the host rock keeps its original magnetization direction. And if we obtain these different directions in the dike and unbaked host rock, that proves that the direction we obtain from the dike is the primary. So this is the baked contact test. We did this for 5 or 4 sites, and in all of the sites we got inconclusive results. And this was mainly because of the unstable nature of the host rock far away from the dikes. So then there is also Ken Bakkan introduced a one more test that he calls regionally consistency test. And in that test, he proposed that if a dike swarm emplaced over a short time interval yields a consistent paleopoles over a large geographical area in the interior of a craton, and if there is no evidence of the regional metamorphism or the secondary data, it's likely that the remanence is primary. And for us, we have sampled also another dike swarm in the same area, 1.1 GA Huila epempe swarm, and we were able to provide proofs, positive baked contact test, that the direction of the magnetization for this Huila epempe swarm is primary, and it is distinctly different from the direction of these Virey dike swarms. So this is Huila epempe pole, and this is our Virey pole. So we are proposing that we have a positive consistency test, and that indicates that this is probably the primary magnetization we are obtaining from the Virey swarm. And then another thing is that the possible reasons for secondary magnetization for the Virey swarm are the nearby Congo and Damara belts. They were originally active in late Ediacaran to early Cambrian times, and these would have been the most likely source of remagnetization in the geological past of the area. And then we are comparing the Cambrian poles of the Congo, São Francisco, with the new Virey pole, and it's distinct to those. So it indicates that we are not dealing with the secondary magnetization caused by Congo and Damara belts. And then there is also one other unpublished preliminary poll from the Kunene complex. This is not, so yes, it's not published. It's coming from honor's thesis work of Tierney Larson from Dave Evans's group. And this poll is overlapping with our mean Virey poll. Okay, so despite the scatter, we are proposing that the poll we obtained from 1.38 Virey swarm is reliable. And then when we are reconstructing Nuna, we start by building up 1.5 GA Nuna model, and based on the coeval large igneous provinces, we are in between Congo, Baltica, and Siberia. We are locating Congo close to Siberia and Baltica. And this reconstruction is done using the quality filtered poles from other Nuna cratons. And yes, as I mentioned, we are proposing a southwest Congo, Siberia, North China connection. And the poles from different Nuna cratons overlap between 1.79 until 1.5 billion years ago. So it indicates that this type of reconstruction is paleomagnetically permissible during that interval. And in this reconstruction, we are also showing Samba, Amazonia Baltica model of Åke Johansson. And as you can see, this is the new Virey pole. So it's very distant from the other coeval Nuna poles. So it indicates that that Congo, São Francisco should have been broke up from Nuna before 1.38 billion years ago. And we are showing a reconstruction of that here. So this is the 1.38 GA reconstruction, and this Virey pole requires a large rotation of Congo in between 1.5 and 1.38 GA. And this also, I also note here that Amazonia is, the poles for Amazonia requires same type of rotation in between 1.5 and 1.38 billion years ago. And in this reconstruction, the location of the 1.38 large igneous provinces are shown with the red squares. And in this, we are proposing that this type of spread of the blips could have been produced by the two separate plumes. So one at the northeastern margin of Baltica, and then the other one at the southern margin of Congo, São Francisco. And these events would be temporally related to the early stages of the breakup of Nuna. And then just to, I'm coming to the end. So I'm just briefly showing you the Rodinia reconstruction here. And to go from Nuna, or the early breakup of Nuna, to Rodinia reconstruction, there are needed very large rotations and displacements. So sort of Congo, São Francisco relative to Laurentia from Nuna to Rodinia needs 180 degrees of rotation. And similar type of rotation is also proposed for West Africa and Amazonia. And it's very hard to accommodate this type of rotations. And but then on the other hand, in our paper, we stressed that such large-scale relative rotations are expected when there is a orthogonal rifting and convergence, which is interspread with transform motion through long time intervals. But then, of course, we are also I want to stress that the number of data for these reconstructions is still quite small. So this is coming to the conclusion. So we were proposing that indeed Congo São Francisco was part of Nuna at 1.5, and then the new pole from the Virey dykes form is showing that the Congo São Francisco was breaking up from Nuna between 1.5 and 1.38 GA. And we are proposing that this new pole from Virey's form is robust. And this is just to show once again how the number of poles for Congo has increased. So 2003 there was no poles, and at the moment we have 4 high quality poles, but the number is very low. So then thank you for your attention, and I want to emphasize that this type of work is always a group work. So you see all my co-authors here in this. So thank you.
All right, thank you, Johanna. We can switch to a question and discussion session. So you can ask either by typing your question into the chat and I can read it aloud for you, or you can find the raise hand button. If you click reactions at the bottom of your Zoom window, the raise hand button is right there. So we'll give a little bit of time for people to formulate their questions.
So Johanna, nice talk. Maybe I just start with a quick question. I guess you, at the time when Amazonia and Congo, São Francisco separated from Baltica around between 1.5 and 1.3, you don't have data for West Africa, so you cannot say if it was separated or how it was positioned.
No, we don't, and we are here just keeping it in connection to Amazonia.
And you imply that Amazonia kind of rotated and came around before Greenville to collide with sort of northwestern part of Baltica, right?
Yeah.
Okay, thank you.
All right. Seems you convinced everybody. Okay, someone in the chat. Sorry, I'm not sure what your full name is. Jamir.
Joe.
Joe?
Yes, Joe. Yes,
Okay, Joe
yes, yes, Joe. They were vertical.
Were the dikes vertical?
Yes, they were vertical at the sites where we able to actually see the contacts. Good question. Thank you, Joe. So this is one that sort of tells that there is no tilting of the block as the dikes are still vertical.
All right, we have another in the chat from Karthik Sender Sarwan. He asks, fascinating talk. Are all minerals equally susceptible to magnetization? And if not, how do you accommodate for this disparity, if the disparity exists?
If I understand the question right, you are asking if all the minerals can be magnetized. We are mainly dealing with the iron oxides in these type of mafic dykes. So usually the magnetite is the primary mineral in these dykes, and we were dealing with magnetite magnetization.
Okay. Ake also asks if you can share references for the papers on the slide.
So the last slide.
Yeah.
So those three that you are showing below. I think at least one or so I have missed, so could be good to check.
I'm sorry, okay, I didn't hear. So these 3 papers?
Yeah.
Yeah, I will send them to you.
Oh, good.
All right. It seems like
So just curious, did anyone look, is where a record, sedimentary record of rifting and breakup between 1.5 and 1.3, or do you have any thoughts about it?
No, we did not look. We
Mhm.
did not look that. But that is something that should be done.
okay. Well, if there's no more questions, it seems everybody's satisfied with your work, Johanna. So thank you.
Thanks,
So
Johan.
much.
All right, it was great. All right, everybody, we only have 2 more before we go for the summer. So we'll see you next week, though.
Actually, I think we might have 3, but so stay tuned. We have one on Hadean, another one talk on Paleomag, and maybe one more on modeling of snowball Earth.
Okay. All right, everyone, take care. See you next time.
See you.